Good.
Is it rolling?
Yes, it is. It is now.
Oh, okay. So today I'm going to be telling you guys about showing these kids about the principles behind Tang, which is this instant orange juice powder from the 90s. I grew up with it. And space ice cream, also known as astronaut ice cream. So a little background. What I would first do is like go and ask around, like who's ever heard of Tang or who knows what space ice cream is, just to sort of garner some interest and some excitement. And then I would give them a basic definition of what it is. So Tang is just an instant orange drink that comes in the form of a powder, and all you do is take like half a scoop, add water and instant orange juice. And space ice cream is basically dehydrated ice cream. It was originally created, a bit of a history, by Whirlpool Industries under a contract from NASA, because they wanted to develop food that would be able, the Apollo missions would be able to take for a long amount of time without the need to worry about a refrigerator. So I would then go ahead and ask the kids like how they think something like this was made, like how they make space ice cream or dehydrated ice cream or dehydrated orange juice. Sort of let them sort of get garner like a basic foundation of what they think this stuff is made from. And then I'm going a bit of, I guess, the scientific background. So each of these things is made from two different concepts, actually. Tang is made from a process known as spray drying, whereas space ice cream is made from a process known as freeze drying. So let's start with the space ice cream first. So at this point, what I would probably do is I would take the ice cream and sort of pass it around to the groups. Let them like get a feel for it, see what it looks like. Then what I would do is like sort of have them hold it up and sort of ask them questions like, what's it feel like? You know, does it weigh a bit? What they think it would taste like. Then I would start going into a bit of the scientific background of the product. So starting, I would first start out with talking about phase changes, because one of the two primary principles behind freeze drying is a phase change. Sort of asking about what they think, how many phases are there out in nature, and so I'd use some examples. For example, water. We go through 3 phases: solid, liquid, gas. Give them visual about give them a visual standard to sort of compare this ice cream to. So in this case, this is a solid, right? And ice cream is usually, it is a solid, it's a little more creamy in consistency, there's a bit of liquid to it. And so the way freeze drying works is they manipulate pressure instead of temperature to facilitate a phase change. So I would first ask these kids, if how they can produce a phase change. So how do you normally get from a solid to a liquid to a gas? And most of them will say temperature. Then I would introduce the fact there's another way to facilitate a phase change, which is through manipulation of pressure. So then what I would do is talk about how freeze drying for this space ice cream works. So what they do is they take a product, right? So for example, they take a slab of ice cream, put it under a vacuum, under a bell jar of some sort, so a vacuum system. And what they do is that they lower the temperature initially. They lower the temperature so much that the remaining water in the ice cream will actually start to crystallize. So it creates these large crystal molecules of water within the ice cream slab. And then once that's been achieved, what they do is they lower the temperature. And they lower it so much that the water crystal actually sublimates. And so the water crystal goes from solid ice to a vapor. And because of that lower pressure within that vacuum system, that vapor is forced out of the solid and out of the ice cream. So at this point, I would kind of explain to them what a sublimation is. So sublimation is a process where a material undergoes a phase change without going through an intermediary phase. So for example, ice going from a solid straight to a vapor. A very easy example to sort of help them visualize would be dry ice. So dry ice is first CO2, carbon dioxide. And at current pressure temperatures, when you take it out and you sort of boil it in a frying pan, what happens is that it actually sublimates. It turns straight into a vapor without going through the liquid phase. Yes, Casey.
What is a vacuum?
So a vacuum is basically a condition where you have lowered the air pressure so much compared to what the normal room pressure is. So for example, if I took this closed system like this, right, stuck a probe in there and sucked as much air out, so much so the pressure in this room is actually more than the pressure inside of this little tub, then that tub is in a vacuum state. Alright? So, I know I've been throwing a lot of I'm sort of trying to stop you in the middle and explain this to you, but I'm saying this so you guys can have an overarching knowledge, so when you guys go through, you can sort of put things together into a more fluid script, right? So you explained the process of freeze drying. You've explained sublimation at this point, and you've explained pressure change, phase change to pressure. Yes.
One more question. So you said that they take ice cream, put it inside of a vacuum chamber, and as they lower the pressure,
first they lower the
temperature to create crystals of water, right? Then they lower the pressure.
Yes.
When they lower the pressure, the ice crystals sublimate and turn into a vapor.
Yes.
And then the vapor gets sucked out of the bell jar or the vacuum.
Because of it's a lower,
Got it.
Yeah.
Got it.
Yeah. So at this point, what I would do is I would have them taste the little slabs of ice cream. So let them pick whatever their favorite is. Ask them, tell them to put it in their mouth, and sort of just start chewing on it. Just let it sit in their tongue, and because what's going to happen is it's going to rehydrate with this fluid in their saliva, right? And this is probably oh cool, how is this working? They're gonna freak out over it, right? So at this point, you can ask them questions like, what's it taste like? What's it feel like? What the experience of trying the freeze-dried ice cream was like. Then I would just ask them some basic questions like, why did the ice cream rehydrate so quickly? And goes ask them around and probe for some ideas. And sort of after you get a sort of a consensus, just tell them their real answers, because within that freeze drying process, right, when that water crystal is created, right, it takes up a large amount of space, right, because all those water molecules are organized into a crystal, and when it sublimates, it leaves this empty space behind. So in this piece of this slab of dehydrated ice cream, and if you have them sort of look at it closely, you can see these tiny pores, and at one point, if you want them to see the pores clearly, you can actually have them lick it, a side of it, and actually show a multitude of pores on the surface of the dehydrated ice cream. And so all these pores are basically cavities that sort of increase the time and how quickly this slab rehydrates. Right? So you have all these empty pockets where water can sort of force itself and interact with the compounds of the ice cream itself, creating a sort of a creamy consistency. Yes, Elijah.
If it's ice cream, why doesn't it melt?
Because the function of the reason ice cream melts isn't because it's ice cream, right? It's basically you've taken a good portion of the composition of ice cream is just water, right? So water, ice cream would have milk, heavy cream, right? All these constituents have water inside of them. Right, so what's causing the melting is not the ice cream itself, but the water that's present in the mixture. So by freeze drying it, you're basically removing all the water, I guess the melty bits of the ice cream, right? And so, yes.
So when they take, first of all, do they use freeze-dried ice cream in space? That's thing one.
Yes.
Thing two, will there be weight reduction benefits, I'm assuming, because they're removing a lot of the water from the material. Now the material becomes very light, right?
Yeah. Right. I'm going to cover that in the end because it's they both are made for the same purpose, just with different processes. So I'll get to that. Moving on to Tang. So like I said, Tang is an instant orange juice drink, and it was very popular in the 90s. Like when I lived in the Middle East, they sold this giant, huge metal tubs that would last you for 2 years. So basically the way Tang works is it's a slow powder, right? And what they do is they take cold water, add it out, and you can see as I'm introducing the water to it, it instantly turns into a liquid, right?
And this will already be done for you all.
Yeah, so this will already be done for you all, and it will be mixed. So the process behind this, creating this powder, is actually very similar but a different principle known as spray drying. So the way spray drying works is that they take a concentrated liquid, right? Because the more concentrate you have, the more non-water particulates that you have, the ones you're trying to isolate from the water you have there. So what they do is they take a nozzle, right, and a nozzle system, and they force the concentrate through this spray nozzle, which creates a mist, right? And that mist is sprayed into this chamber that has extremely hot and dry air running through it. And what happens is, as that liquid is being sprayed, right, so when it gets sprayed, it turns these little individual droplets that are very almost microscopic, right? And as the dry air comes through, it vaporizes all the water or the water particulates within the individual droplets, leaving the powder behind. So from a visual scenario, what happens is you have this chamber, hot dry air is running through it, liquid concentrate gets sprayed, and as you see it drop to the surface of the chamber, all you see is a dry powder, right? And the science behind this is we're basically manipulating the size of what you want to vaporize, right, in this sense. So if you, for example, ask them, does it take longer for a drop of water to evaporate versus like a huge puddle of water, right? The answer is it takes less time for the drop of the water to evaporate, right? And so if you, for example, another way you can, just going a bit in depth, you can do is you can take, let's say, a couple of droplets of water and water droplet that you have smeared across the table, right? And the water droplet that you smeared across the table evaporates faster because what you've done is you sort of increased the surface area with which the air can come in contact with, right? So what you're doing is when that mist of concentrate gets sprayed, those individual droplets, there's a lot more surface area for that air to come through and remove the water from that individual droplet, right? And that's how a product like Tang is created. Now, two different processes, two different products, but they're all made for the same reason, right? So to go and ask these kids at this point and ask them questions like, well, what is the benefit of having this instant mix, right? And gather some answers. The correct answer is because, well, it has a longer shelf life, so it lasts longer, right? Like this freeze-dried ice cream would probably last maybe a month, would last years compared to just like normal ice cream, right? Same with Tang. So also you don't need to refrigerate this, right? So in many countries, they don't know how to refrigerate this at all. Additionally, in space, taking things up into space, it's a very delicate process. You want to make sure that everything you take up, it's absolutely necessary, right? So weight is a big issue in doing space flights, right? So if you can remove all the water from a product, you've increased its shelf life, you've increased, the way you can store it. You don't need to refrigerate it. I can just leave it there in a random pantry, right? And you've drastically reduced the amount of weight, right, that it carries. So at this point, I would just go around and ask some preliminary, some just finishing questions like, who do you think, something like an instant product would, benefit? Like for example, places where they don't have refrigeration, right, or places where they don't have access to foods, perishable foods such as, milk and oranges, where then instead they can use a powder form and create whatever they want without having to worry about it going stale. Then I would ask them for when it comes down to, I guess, the freeze drying principles. I'd ask them stuff like, would it take longer for water to boil at sea level, or up on top of Mount Everest, right? The correct answer is, water boils faster on Mount Everest than sea level because there's less atmospheric pressure acting on the fluid at that altitude versus at sea level. And then I guess just a trick question you could ask them, would it take longer for an egg to cook completely at sea level or Mount Everest? Sort of garner some, whatever their responses are. And most of them probably say it would cook faster in Mount Everest because they think, okay, well, boiling time is reduced. Well, the actual answer is it actually takes much longer for an egg to cook completely through Mount Everest, and that's because every food has a certain temperature it requires to cook to, right? So it's going to take you longer for you to reach that temperature at Mount Everest versus at sea level.
Why?
Because water in and of itself, you're looking at two different principles.
Mhm.
You're looking at reaching a certain temperature threshold versus, vaporizing or, changing phases between two materials, right? So an egg has a higher temperature threshold than boiling water does.
So water doesn't actually, when it's on top of Mount Everest, it boils at a lower temperature, right?
Yes,
So-
technically it boils at a lower temperature and a lower pressure.
Right.
Right, phase change is a function of both pressure and temperature. Right, if you're more analytical about it, what's happening as you're boiling water in Mount Everest, because there's not a lot of atmospheric pressure, there's not a lot of pressure sort of pressing against the fluid, right? Which means it doesn't take as much energy for those molecules to get excited and turn into vapor, and so vaporization happens when the energy in the pressure exerted by the liquid molecules is equal to the pressure exerted by the surrounding environment. So there's that.
So for eggs, if an egg needs to have an internal temperature of 190 degrees Fahrenheit, which I don't even know if it would,
Yeah.
but if you're on the top of Mount Everest, it would take a lot more energy to get that egg
Yes.
to reach that temperature due
Yeah.
to the fact that the water boils at a lower temperature than it normally would.
Yeah, you have to keep adding water to
Right.
facilitate that cooking
Got it.
process.
Do they still use either of those in space?
No, not anymore. And actually, yeah, they do. They don't use Tang, these powdered substitutes anymore. And the reason is you can turn this into a question. Ask them feel some answers like, why don't they use this anymore? And the reason being, so for example, the easiest way to examine this piece of ice cream. If you break it apart, right, there are these solid particulates that are released into the atmosphere of the space station. And these particulates, if they get into electrical components, and these electrical components are very fragile, right? It can mess things up out in space. You're only one mistake away from death. So you don't want something like this. Nowadays they use liquid or liquidized food instead because it's much more controllable.
It turns into a
Yeah.
sphere when it's released.
Yeah.
Cool.
Awesome.
Perfect.
Done.